What is kinetic energy? अभी थोड़ी देर पहले बात किया ना. Kinetic energy is due to the motion of an object. So this energy arises when the object acquires velocity. Symbol आप K से लिखो या KE से लिखो, we call it as kinetic energy. Most common is KE. The formula or expression for the same, you know, it is half mv square in all the cases. In any of the cases it is half mv square. बोले all the cases नहीं, यहाँ पे भी थोड़ा सा चेंज हुआ ना अभी. हाँ, when the molecules of the gas are in motion, तो वहाँ पे ये थोड़ा सा बदलता है, वहाँ पे थोड़ा सा बदल जाता है, वहाँ पर एक नया स्पीड आ जाता है. we call it as root mean square speed. तो speed but will remain associated. Speed but will remain associated in the expression of kinetic energy means wherever you have kinetic energy, the cause is the motion of the object or the molecule, right? So these are two categories of energies which we need to study, and we need to study their interrelation, their correlation with the work done. Now how the energies are related to the work done? See, there is a theorem. जिसको कहते हैं हम लोग वर्क एनर्जी थ्योरम, जिसको कहते हैं वर्क एनर्जी थ्योरम. तो व्हाट इज वर्क एनर्जी थ्योरम? Suppose there is a force which displaces a body, means work is done on the body. So suppose there is a force acting on the body and the force displaces a body, then in such a situation the work done on the body is equal to the change in the kinetic energy of the body. That is the work energy theorem. I'll write it down. What is work energy theorem? The theorem states that if a force produces displacement in a body, then the amount of work done is equal to the change in the kinetic energy of the body. See, I can write this as, that is, work done equals to change in kinetic energy delta K. Do we have a proof for this? Yes, we can prove it. ठीक है? See, the small amount of work done on an object is given as what? F dot ds. We can write it as F ds if theta equals to 0 degrees, since cos 0 is 1. Correct? Now, split up force. What is force? It is mass into acceleration. Substitute करिए इसको. Substitutions I am putting them with a different color so that they are a bit highlighted, you know. So F equals to ma. Substitute this. If you do that, you will get it as dw equals to ma into ds. Then one more substitution. What is acceleration? Defined as rate of change of velocity with respect to time, or we can write it as dv by dt. If I substitute this again, what I'll get is dw equals to m dv by dt into ds. Further I can write therefore dw equals to, थोड़ा सा rearrangement, m ds by dt. Take ds inside the bracket over the as the numerator and take dv outside. So ds by dt, rate of change of displacement with time is velocity. You can write it as mv dv. Correct? You can write it as mv dv. क्यों लिखा? Substitution क्या है? It is v equals to ds by dt. ना? So now to get the total work done, integrating both sides with proper limits. So if I integrate both sides, on left hand side is integration dw, mass being constant taken outside integration, integrating v dv from initial velocity u to, लिमिट्स को कुछ और कलर से लिख देते हैं, फ्रॉम इनिशियल वेलोसिटी से u टू फाइनल वेलोसिटी v, तो इसको u to v कर देते हैं. मीन्स व्हेन द वर्क इज डन ऑन द बॉडी, the speed of the body changes from u to v. So you can write this as m. Integration will give you v square by 2 from u to v. Apply the limits, upper minus lower. dw integration is w m by 2. 2 पे तो लिमिट लगेगा नहीं. Upper limit v square minus lower limit u square. This is half mv square minus half mu square, correct? So final kinetic energy half mv square minus initial kinetic energy half mu square. Hence, your work done equals to change in the kinetic energy. Proved, na? So this is how mathematically you can show that the amount of work done, if the force displaces the body, then the amount of work done in the process can be also obtained as a result of change in kinetic energy of the body. As a result of change in kinetic energy of the body. Right. Now after this, I will highlight you a principle that is very common principle, very famous principle known as interconversion of energy. Known as interconversion of energy. You know, energy is convertible. It can neither be created nor be destroyed, but it is convertible from one form to the other. Means potential can be converted to kinetic and kinetic can be converted to potential. ठीक है? Kinetic can be converted to potential. ठीक. चलिए काम करते हैं, इंटरकन्वर्जन ऑफ एनर्जी को समझते हैं. अब इंटरकन्वर्जन ऑफ एनर्जी बेस्ड किस पे? द प्रिंसिपल इज दिस phenomena of interconversion of energy is actually based upon, basis is what? Basis is law of conservation of energy, which states that energy can neither be created nor be destroyed. So what I'll do is I'm going to highlight this to you in a system of oscillations of spring mass system. इसका क्या मतलब है? इसका मतलब है वर्टिकल और हॉरिजॉन्टल किसी भी अलाइनमेंट में आप एक स्प्रिंग ले लीजिए. सपोज आई एम टेकिंग इट इन द हॉरिजॉन्टल अलाइनमेंट. ठीक है? Now you can either elongate it or you can compress it. So this is stage 1, S1. Whatever the stages are of the spring, we are going to plot its energy with respect to the displacement. This means that this is a graph that is going to be drawn as, energy of the spring, that is total energy of the spring versus x, that is the displacement, or you call it as elongation or compression of the spring, x. Right? They can either displace the spring on the left hand side or on the right hand side. Therefore, the graph is being shown on the negative side as well as the positive side with respect to the natural length. मान लो natural point is this one, na, O. So we can either compress the spring, we'll be plotting that compression on the negative side, and we can either elongate the spring, so we'll be plotting it on the right hand side, on the positive side of the x-axis. ठीक है? Now naturally, since the total energy has to be conserved, so let the total energy of the spring be given as E. be given as E. The total energy of the spring, यहाँ पे नहीं लिखूंगा. This is the total energy, line showing total energy, right? Now what will happen initially when there is no elongation or compression in the spring? तो अभी तो ये नेचुरल स्टेट में, बट अब क्या करते हैं आप? You apply the force F and you try to pull it to an elongation, say X. So spring comes to state 2, and state 2 can be represented like the spring gets elongated a bit, say by what amount? तो यहाँ से एक स्ट्रेट लाइन ड्रॉ करते हैं. Let the elongation cost be X. So in this state, when the spring has been elongated by amount X, say this is the extreme position and the elongation is X. Since it is on the right side, मान लीजिए this is plus X on the displacement axis. So corresponding to plus X, the potential energy at this point will be half kx square, while the kinetic is going to be 0. Because we have stretched the spring and the spring is at rest now. So kinetic will be 0 and potential will be maximum, that is half kx square. Potential will be maximum, that is half kx square. Now if you leave the spring right from here, what will happen? X will go on decreasing. And potential energy will also start decreasing. Result, the value of kinetic energy will go on increasing. Then there will be a moment in state 3 where the spring will be in its natural length or will be crossing the mean position again. तो mean position के लिए एक reference line बना लेते हैं, blue one, ठीक है? So my spring is crossing this mean position again. So when the spring is crossing the mean position, your x becomes 0. Elongation is 0. Therefore potential energy is 0. ये गई कहाँ? Converted to whole amount of kinetic energy. Value again half kx square, because the total energy remains conserved or constant. Shown by E, that is half kx square. फिर क्या होगा? Will the spring stop here? The answer is no. Due to inertia of motion, the spring is going to cross this position and reach state 4 and will be compressed by some amount. कितना? वो देखते हैं. The compression will be again what? By amount X. If we consider the ideal situations where no loss of energy is taking place, therefore the spring will go on compressing until its velocity becomes 0, until its kinetic energy becomes 0. So kinetic energy will become 0 if the velocity of the spring becomes 0. तो velocity जैसे 0 होगा, spring रुक जाएगा, लेकिन उस समय it will be compressed by amount X. Therefore kinetic energy in this state is 0, while the potential energy becomes half kx square. You can see potential again becomes maximum. So again, at the one of the extreme positions, when the displacement is minus x, you see minus x, what happens? Potential energy becomes maximum. यहाँ पे हम कहेंगे displacement is minus x because it is on the left hand side. यहाँ पे हम कहेंगे displacement is plus x because it is on the right hand side. This is the elongation shown by positive sign and this is the compression shown by negative sign. तो दोनों ही states में, whether the spring is compressed or it is in the elongated state, the potential energy is maximum and given by half kx square. So corresponding to these two positions, we get the maximum point, that is half kx square. E shows half kx square. So मुझे एक coordinate ये मिलेगा, एक coordinate ये मिलेगा. And when x was 0, potential energy was 0. The third coordinate is my this. This is the point where x equals to 0, na? So now if I connect these 3 points, the curve is going to be parabolic. The curve is going to be parabolic because this is a second degree equation with respect to energy. You see this is a second degree equation. Therefore, it is going to be a parabolic graph and this curve will show you the trend of potential energy. मैं इसको U लिख देता हूँ, equal to नहीं, because it keeps on changing. Rather I should write E equal to half kx square. That is the line showing the maximum energy, right? Now let us plot the trend of kinetic energy. Kinetic energy को जरा ध्यान से देखिएगा. When the x was 0, kinetic energy was maximum equal to half kx square. That means at x equal to 0 kinetic energy is maximum. So blue coordinate मुझे यहाँ मिलेगा. The blue coordinates correspond to the kinetic energy. But when the compression is x or the elongation is x, you see the kinetic energy is 0 at both the points. So at minus x, that is compression state or fully compressed state, or the fully elongated state, the kinetic energy is 0. So if I connect these 3 points, again it will be a parabolic relation. This will be the graph showing me the trend of kinetic energy K. Okay? So blue curve shows kinetic energy and your black curve, both are parabolic, remember that, shows the potential energy. So this is how this oscillation of spring mass system is understood. The curve drawn on the along side shows you the conservation of energy principle, shows you the conservation of energy principle in a particular category, that is spring mass system, right? इस तरह से आप किसी और सिस्टम को भी ले सकते हैं. फॉर एग्जाम्पल यू कैन टेक अप विद say we are dropping a ball and it is rebounding again and again to the same height in ideal conditions. So उसमें भी हम बात कर सकते हैं. तो wherever we are talking about energy, we can again plot the graph, but वहाँ पर जो ग्राफ आएगा that is going to be a straight line. वो हमें इक्वेशन देखना पड़ेगा पोटेंशियल एनर्जी और काइनेटिक एनर्जी में और डिस्प्लेसमेंट में क्या रिलेशन आ रहा है. इफ इट्स फर्स्ट डिग्री इट इज गोइंग टू बी अ स्ट्रेट लाइन, इफ इट इज सेकंड डिग्री इट्स गोइंग टू बी पैराबोलिक एंड सो ऑन. ठीक है. सो दिस वाज the parabolic relation because we obtained potential energy as x square, function of x square, or kinetic energy as function of x square. So in both the cases this was a parabolic relation being a second degree equation. ठीक है. That's all with the conservation of energy. This is your second video or second leg in chapter work by energy. The last leg still left, we'll talk about collisions, but that is in the last leg. That's all for today. Do go through the video. Any problems in any of the formulae used in this particular video, just refer the first one. Thank you.